Welcome to the another session on engineering mathematics 4. Mathematics 4. Today, I will revise all the concepts of first unit here. First unit so far we discussed here. Discussed. We'll revise the all the concepts here, and then tomorrow it will be useful for your tomorrow examinations here. Yes, wait a minute. On the unit 1 revision of unit 1. Partial differential equations. Partial differential equations. The first concept we started with that formation of PDE, PDE by eliminating arbitrary constant. Eliminating arbitrary constants. And the second one is by eliminating arbitrary functions. Arbitrary functions. For that, you have to differentiate. The procedure is that you have to differentiate given relation. Differentiate given relation partially with respect to x and y. Partially with respect to x and y. Differentiate given relation partially with respect to x and y, and eliminate arbitrary constant and arbitrary function. And arbitrary functions with the help of these derivatives. The help of these derivatives. That will be the idea we can get there. The procedure is that you have to differentiate given relation. You have to differentiate given relation partially with respect to x and y, and eliminate arbitrary constant and arbitrary functions with the help of these derivatives. Eliminate arbitrary constant and arbitrary function with the help of these derivatives. The help of these derivatives here, and you have to substitute the constant relation, or you have to substitute the arbitrary function relation in the original equation. You can get that. This will be the idea. You can get that. This is formation of PDE in the first chapter. You can see that. For that, you can use the relationship of P is equal to dou z by dou x, and Q is equal to dou z by dou y. Dou z by dou y. Then R equal to dou square x by dou square z by dou x square. S is equal to dou square z by dou x dou y, and T is equal to dou square z by dou y square. Dou y square. These are all some standard notation we can use in order to eliminate arbitrary constant, arbitrary function, and in order to form the partial differential equation also. Partial differential equation also, that is the thing we can follow. And then second concept, we consider that solution of PDEs. Solution of PDEs. Solution of PDEs. That will be the second one. We consider. Second one we consider as a solution of PDEs. Solution of PDEs. The solution of PDEs First, we concentrate on by direct integration. These are all simple procedures. Simple procedures. Direct integration, and first one direct integration, and then second one is that first order non-linear PDEs. Okay, first order non-linear PDEs. Non-linear means higher degree. Higher degree. Here we are going to consider first order non-linear PDEs, first order high degree PDEs. And then higher order, you have a Lagrange's linear equation, first order, first degree. First order, first degree, that will be Lagrange's linear equations. Lagrange's linear equations. Linear equations. That will be the another one. And fourth one is that solution of PDE. In the solution of PDE, higher order PDEs. Higher order PDEs of homogeneous type. Higher order PDEs of homogeneous type. Okay, these are the four different type of 3Ds and their solutions we discussed here. Okay, and their solution we discussed here. By direct integration, first order nonlinear PDEs, first order first degree PDEs, and then higher order PDEs of homogeneous type. Okay. What way we can proceed? What are the methods we consider here? In the direct integration procedure, if we have only one derivative in that equation, if we have only one derivative, okay, only one derivative in the given equation, okay, in the given equation, we can adopt this procedure, direct integration. We can adopt this procedure. Okay? We can adopt this procedure if we have only one derivative in the given equation, then we can adopt this procedure of direct integration. Direct integration. Then when we concentrate on first order non-linear PDEs, okay? First order non-linear PDEs, solutions classified into four ways. Classified into four ways. One is complete solution. Second one is general solution. Third one is particular. And the fourth one is singular solution. Fourth one is singular solution. When you concentrate on first order nonlinear PDE, solutions classified into four ways. When can you say that a solution of PDE is a complete solution here? Can anyone have the idea?
Number of arbitrary constant equal to number of variables in that.
Yes, very good. Number of constants is equal to number of independent variables. Okay? Number of independent variables of that equation. Number of independent variable of the equation, that will be the complete solution. General solution, number of constants equal to
Degree of
Order of
order
PD.
order of the PD, equal to order of the PD. Equal to order of the PD. Order of the PD is one. You have to get only, if you have only one constant, it will be treated as a general solution. Number of independent variable x and y, x comma y. Then you have two constants here. You can say that number of complete solution. Okay, complete solution. Particular values to general or particular values. Putting particular values in the complete solution. In the particular values to the arbitrary constant. Putting particular values to the arbitrary constant in the of complete solution. To the arbitrary constant. The arbitrary constant of particular complete solution. Complete particular values to the arbitrary constant of complete solution will be. Can anyone have the idea of singular solution? Singular solution.
Envelope of family of curves, sir. We should
Envelope of
differentiate with respect to
uh,
arbitrary constants to eliminate.
very good, very good, very good, very good. It will be nothing but envelope of general or complete solution here. Envelope of general solution or complete solution here. It can be obtained by differentiating partially with respect to the arbitrary constant of complete solution or general solution. Differentiate partially with respect to the arbitrary constant of complete solution. If we have two arbitrary constants, we can differentiate partially with respect to A and with respect to B, and from that you can get the relationship of A and B in terms of X, Y, Z. Then substitute that. That will be the idea. Therefore, when you concentrate on first order nonlinear PDEs, the solutions are classified into four ways: complete, general, particular, and singular solution. Complete solution or general solution or complete solution. Okay? This will be the idea we can follow. Now, in the first order nonlinear PDEs, we have standard four types. We have standard four types. We have standard four types here of equations. First one is that f of pq is equal to 0. F of pq is equal to 0. F of pq equal to 0. Second type is that f of separable equations. F of x comma p equal to g of y comma q. And then third type we consider as a Clairaut's equation. That will be y is equal to px plus qy z
Is it
z. Yeah, z equal to px plus qy f of pq. F of pq. And fourth one is f of z pq is equal to 0. F of z pq is equal to 0. This will be the four types of equations we consider that. Okay? Four types of equation we consider that. When you discuss the solution of this type of equation here, complete solution, how can you determine the complete solution and everything for this type of equations here? Solution complete solution is z is equal to
px
ax
plus
plus y plus c, where a and b are related by where a and b satisfies f of a b is equal to 0. This equation we satisfy this equation f of a b equal to 0. Therefore, we can write b in terms of f of a. B in terms of f of a. And the general solution you can write as usual here. Replace b is equal to pi of a. C is equal to pi of a. Pi of a. No singular solution for this type of. No singular solution. No singular solution for this type of problem. This is general solution. And here this is separable equation. This equation is called as a separable equation. Here you can write p in terms of function of x comma a by taking a say. What is the idea here means we can able to separate x comma p one side in a given equation. If you are able to separate x comma p one side and y comma q other side here, then you can call them as a separable equation. For this, you have to put equal to ASA. This proportion, this ratio is equal to ASA. And then from that, you have to identify P in terms of x comma a from this relation. Similarly, from this relation, you have to identify Q is equal to a function of y comma a. Then complete solution is given by z is equal to by total derivative area q dy pdx integral pdx plus qdy plus an arbitrary constant c plus an arbitrary constant. Because of this C plus C extra, no singular solution. General solution is put C is equal to pi of A. Put C is equal to pi of A, no singular solution. If you keep this plus C as it is here, you can say that no singular solution here. No singular solution. For that type of way, you can identify it. This is separable equation. The first type is there is no x, there is no y, there is no z, only p comma q. If you see in that equation only p comma q present in that equation, then you can say that will be a first type equation. Okay? First type of p comma q equation. You can see x p y q in that equation. You can see x p y q in that equation. But able to separate xp one side, yq separate another side here. Then you can say that you can proceed by this way. This is Clairaut's equation, standard form. Clairaut's equation here. Clairaut's form of equation. Z equal to px plus qy. Z equal to px plus qy. Z equal to px plus qy plus f of pq. F of pq. It is Clairaut's equation type here. Clairaut's equation type. Here, complete solution just replaced by pq by ab. Ax constant, arbitrary constant. Ax plus by f of a comma b. F of a comma. Put p is equal to pi of a, then it will be general solution. Singular solution for this type of problem, singular solution is possible. That is very important to identify. Possible. That you have to identify for this type of equation. Clairaut's equation type only you have to identify singular solution importantly by eliminating arbitrary constant a and b in the complete solution. Differentiate partially with respect to a, partially with respect to b. Then we have to eliminate arbitrary constant from that. For that, you have to write a b in terms of x y. For that, you have to this is px plus qy. Any equation, even though it is not in this form, but if you are able to convert this kind of form, then you can say that px plus qy f of pq is Clairaut's equation. And then fourth type is f of zpq. In an equation, if you are able to find zpq only here, zpq there is no x and y explicitly, there is no x and y explicitly, then it will be f of zpq equal to 0. What about your idea for this complete solution here?
Z equals to F.
Z is equal to f of u, and where u is equal to x plus ay. X plus ay, a is an arbitrary constant, is the complete solution. Is the complete solution. After this, if you write like this here, then you can write dz by you can write dou z by dou x. That is p as a dz by du. P as a dz by du, and q as a dz by du. A dz by du. It becomes ODE. ODE. Then solve that. It becomes ODE. And solve it. Under this substitution, is equal to f of u is equal to x plus ay. You can get this value of p. P is equal to can be converted as a ODE, ordinary derivative dz by du. Q can be converted as a dz by du, ODE here, and we can solve that. These are the ideas we can get that way. So here you can write general and singular solution can be found as usual. As usual.
So singular solution not possible.
Singular solution
Not possible, right?
not possible. Sometimes suppose not plus c comes here, you can, if you multiply the plus c with the power here, then you can say, therefore generally you can write general and single solution can be found as usual. Okay. For this type you can write this kind of statement only, no need to specify. But Clairaut's equation you have to specify everything. First two types there is no singular solution. You can put only general solution, complete and general solution here. For this type of way, you have four different type of equations. Four different type of equations for this type. For this type. First type, second type, and third type, and then fourth type. And these are the four standard types. Four standard types of first order nonlinear PDC. First order nonlinear PQ only, but P square, Q square, that is possible. P cube, Q cube, that is also possible here. But order is one. Order is always one here. Order is always one. That will be the idea we can follow. I think all of you remember these ideas here. And then we have a conversion of some equation into standard type. Conversion of equations here. Uh, equations equation reducible to standard form. Equations reducible to standard form. Equations reducible to standard form. We have furthermore in first order nonlinear equation. We have under this we have equations of the form f of x power m z power k p y power n z power k q. K q is equal to 0. That is first type, first this one. And then second one is that only z power kp, z power kq equal to 0, or you can write z power kp, z power kq, x comma y, x comma y separate one. And the third one is only x with the product, x power mp, y power nq equal to 0, or z is a separate one. Z is a separate one. X power mp, y power nq, comma z equal to 0. Z is a separate one. Z is 0. Now, under for these type of equations, that can be converted into any one of the standard type here. Here, what are the substitutions we have to put here under some substitution? X, because x and z with the product p, y and z with the product q here. Therefore, we have to put all the substitutions here. Capital X is equal to, we are going to put that x power 1 minus n if n is not equal to 1, or log x, log x if n is equal to 1, that kind of substitution. Similarly, capital Y is equal to y power 1 minus m, m, x power is m, y power 1 minus n not equal to 1, and log y, n is equal to 1, n is equal to 1. And z gets a substitution, z power 1 plus k, z power 1 plus k, for k not equal to minus 1, log z for k equal to minus 1, log z for k equal to. Under this substitution, we can get correspondingly changes in p, q, capital P, capital Q, capital P, capital Q. These equations can be under this substitution. These equations can be converted into f of p comma q, first type, f of p comma q equal to 0, where capital P is equal to dou capital Z by dou capital X. Capital Q is equal to dou capital Z by dou capital Y. Then how can you get this Z and this P and Q from this idea? Dou capital Z by dou small z by dou small x, dou small x by dou small capital X. That matter, because all the x, y, z gets the idea. So under this substitution, you can get this idea. Similarly, we have another type here. But you see that second type, second set of equation, f of z power kp, z power k, z with the product p, product q. Here is also x and y are separate expressions. X, y expressions are separate, not in the product here, not in the product with p, q. Okay? And also very important that you must have p power 1, q power 1 in all the product here. Okay? So depends upon that you have to get a common power here. You have to get the common power and so on. Therefore, for this type of equation, only z only with the product. Therefore, this is the only substitution you have to put. Okay, z equal to so on. The same substitution you have to put here. Okay, same substitution. Now, under this substitution, it can be converted as f of pq is equal to 0. F of pq equal to 0, or separable equation f of x comma p is equal to f of g of y comma q, separable equation. This is separable equation. If this is only means pq equal to 0, where what about p capital P here? Z only gets substitution here, or Z converted as a capital Z. Remaining things are same. Y x is, there is no conversion. X is x only here. Okay? X is x only. There is no conversion. Z only you have the conversion of capital Z. Capital Z. And Q, the same manner here. Z only takes conversion. Y only. Okay. Then how can you get this dou Z by dou X? Yes, Z gets this kind of substitution. Therefore, dou Z by dou small Z by dou X is small p, standard letter p. Well, dou capital Z by dou small z by dou y is small q, that manner. Yes. Now here is also x with the product p, y with the product p, but z is a separate expression. No, z is a separate expression. You cannot get everything in the product here. A common thing in the product here, and in that case, you have to put these two substitutions here. This one and this one. Only x y substitutions only. These two substitutions here. Here you have to put x and y substitutions only. X and y substitution. Therefore, x and y substitution means p comma q, p comma q, or zpq form here. Therefore, it is can be, these equations can be converted as f of pq equal to 0, or f of zpq, or f of zpq equal to 0 here. This is first type, second type, first type or fourth type here. Right? F of zpq equal to 0 here. Therefore, in that manner we can convert. Under this, we have the p comma q. P z no change, but x we have change. Similarly, q z no change, but y you have change. How can you get dou z by dou small x by dou capital X? In that manner we can proceed. Dou capital X. Similarly, q, how can you get q? Dou small z by dou small y, and dou small y by dou capital Y. Always dou small z by dou small x under in all the substitution, we have to always use dou small z by dou small x as a small p. This is small q. Therefore, this is standard notation we are going to use always in this standard. Then only you can replace pq. Then only you can replace. Therefore, this standard notation you have to use always. You have to use always. This is, therefore, this type of equations can be converted into standard type, any one of the standard type, with the help of the substitution. This is the common substitution. Common substitution. X with the product with the p, y with the product with the q, you can use this two. Z only with the product p, you can use this one. So in that manner we can proceed. In that manner we can. So this is the idea you have to think about to convert a standard type. Convert the given equation into standard type. Okay. This is first order nonlinear PDEs. First order nonlinear PDEs that we can consider. First order nonlinear PDEs. I think all of you remember these ideas here. Then we have the direct integration, first order nonlinear PDE. So then we have first order Lagrange's linear equation, higher order PDE. Lagrange's linear equation, higher order PDE. Another one is that Lagrange's linear equation. Equations of the form PP QQ is equal to R, where PQ are functions of x, y, z. are constant. Small q is derivative. Dou z by dou x, standard notation, q is equal to dou z by dou y. To evaluate this one, you have to form auxiliary equation. Dx by, this is always important. Dx by p, dy by q, and dz by r. Okay, dz by. This is function of x, y, z are constant. PQ R. Therefore, you have to form an auxiliary equation that is very, very important. Get solution for Lagrange's linear equation. And then after you have to get two solutions here. You have to get two solutions here. By taking either by method of separation of variable, you have to get two independent solutions, u and v. Okay? Two independent solutions, u and v, from the above three proportions. Above three proportions. Uh, Either by variables are separable, either by variables are separable. Number two, by what algebra proportion. Algebra proportion. And number three is Lagrange's multipliers. Lagrangian multipliers. You have to choose LMN and L dash M dash N dash, such that LP plus MQ plus NR equal to 0, L dash P plus M dash Q plus N dash R equal to 4. Uh,
Sir, should always L be in terms of X, sir? Is it any rule like that?
Sometimes X, Y, Z, sometimes number. Both are numbers. One
But
time
L
variable.
should be in X only, every time. X or either X or 0. That's all constant.
X are constant or any variable, not only necessarily X.
Y comma Z also is possible, sir.
But here mostly you can get X only. Sometimes constant. That's up because you can get LDX plus MDY. Therefore, integrate with respect to X only. It is possible. For mostly 90% X and sometimes constant. That manner can get. I think we solved one problem like this here. XY minus 1. One of the element is xy minus 1. Another problem is solved that minus 1 to 1 in that manner also, constant here. For yes, LDX, MDY plus NDZ we are going to form. Definitely you cannot get in terms of y. Here also you cannot get in terms of YZ, XZ, and XY form. That is the idea we can follow. Okay? Mostly X, and here is also Y, and here is also in terms of Z. Because LDX plus MDY plus NDZ only you are going to get. Okay? Understand? Okay. Therefore, variables are separable. Or algebra proportion. Algebra proportion means dx plus dy minus dz, anything, dx minus dy or dy minus dz. Depends upon the expression you can follow. Lagrangian multiplier is also is one of the algebra proportion idea. But we are going to think to get 0 here. LP plus MQ plus NR equal to 0. L dash P plus M dash Q and so on. With the help of this, you can get LDX plus MDY plus NDZ equal to 0. That is the idea you can follow. Then general solution for this type of Lagrange linear equation is function of u comma v is equal to 0. Function of u comma v is equal to 0. That is right. From this you can get L dx plus M dy. From these two equations you can get L dx plus M dy plus N dz equal to 0, and similarly L dash dx plus M dash dy plus N dash dz equal to 0. 0. Depends upon L m n, you can integrate. So depends upon L dash M dash N dash, you can integrate, you can get solution. Solution. That will be the idea. Okay. So this is the idea of Lagrange's linear equation. Lagrange's linear equation. Then after that we have the concept of higher order PDEs. Higher order PDEs. Higher order PDE is a homogeneous type. Homogeneous type means each and every time gets the same order. Same order. Suppose we start from d square means second time if you consider means d dash 1 plus 1 2. Similarly here d dash d, that's 1 plus 1 2. End time end with d dash. Suppose if you miss that time also, that is also not suitable. 2 2 2 order 2 2 2. If you miss this time also, that's suitable. Get 2 2 2. Or you can miss these two, you can get this one. Is okay. But each and every time in your assignment I gave some problem that is not homogeneous type, non-homogeneous type also, but why I have given that problem is just idea only. You are going to get that procedure only for that purpose. And assignment I gave some problems that is not in the at one stage you can get d plus d dash. It is not homogeneous. It is not homogeneous. It has 1 2, 1 plus 1 2. This is 1 1. It is not homogeneous. It is wrong. Non-homogeneous type. Non-homogeneous type. It contains different methods, but in your textbook contains all the problems. Homogeneous, non-homogeneous type, all that. But in your syllabus you have only homogeneous type only. Therefore, you concentrate only on homogeneous type. This type of equations only. No need to concentrate. I have given this type of problem just for practice only. Because we are going to replace what are the substitutions only. Substitution. For you cannot get same answer in the complementary function. Complementary function here. For don't follow homogeneous type, non-homogeneous type here. Follow only homogeneous type. For assignment I gave some one or two problems like this here. You can see the difference in the complementary function here. Therefore, don't afraid of a complementary function is totally different in the answer in the textbook here, because of it is non-homogeneous type. This is non-homogeneous type. This is the idea. For homogeneous type means each and every time have the same order here, where d stands for dou by dou x and d dash stands for dou by dou y. Dou by dou y of z. Z means dou z by dou x, dou z by dou y, that type of thing you can get equal to function of x comma y. Function of x comma y. These are the homogeneous type here. This is homogeneous type. This is non-homogeneous type. Non-homogeneous type. It's common z and then f x comma y. All of you understand, I think, that difference between homogeneous non-homogeneous type. Non-homogeneous type. Homogeneous means each and every time should have same order. 2, 1 plus 1, 2, 1 plus 1, 2, 2. In that manner can get each and every derivative. We have RHS 0 means complementary function only. RHS 0 complementary function is the general solution. Complementary function depends on the roots of auxiliary equation. This depends on auxiliary equation roots. Auxiliary equation roots. Auxiliary equation formed by d by m and d dash by 1. D by m and d dash by 1 are equate to 0. Equate to 0 again. Equate to 0. Roots of auxiliary equation that constitute the complementary function here. It is of the form pi 1 of y plus m on x plus pi 2 of y plus m2 x and so on. It depends on how many roots you have. How many roots you have. If roots are equal, two roots are equal, you have to put one x. Three roots are equal, you have to put one more x square, x, pi 1, x, x square, m1, m2, etc. Complex roots just replace alpha plus I beta, alpha minus I beta, and so on. Or complementary function,
Solving non-homogeneous is same as homogeneous, sir. How
no,
to
no,
solve?
non-homogeneous is a different idea. It's not in the form of homogeneous type here. I have just given only for replacing the idea, whether you are remembering replacing idea and so on. Particular integral okay, but the complementary function it will be different. Understand? Particular integral
What
is
we
a,
should replace, sir?
what will be,
What is the replacement here, sir?
that will be different, but not this not in your syllabus, so no need to concentrate. Okay. Complementary function only vary, therefore, but it's not in your syllabus, therefore no need to think about the condition for a complementary function. It comes in terms of exponential form or replace. No need to concentrate. For auxiliary equation, complementary function only different here. Complementary function that is for homogeneous type. You have to replace d by m, d dash by u. Non-homogeneous type, no need to think about that. You can leave as it is. Okay. Pi 1 y plus m1x, y plus mnx, and so on. And exponent, sorry, equal root means pi 1, x pi 2, and x square and pi n. Imaginary roots means alpha plus I beta, alpha minus I beta, and in that manner we can replace. What is the idea? Particular integral, that will be cases of different 5 cases here. Case 1, type 1 is f of x comma y, RHS f of x comma y. Depends on RHS f of x comma y. RHS f of x comma y. The first type f of x comma y is exponential function. Second type is f of x comma y is cosine or sine ax plus by or sine of ax plus by, in that manner. Third one, basic, these are all the basic 3 types here. F of x comma y is algebraic polynomial. For this, replace d by a. Particular integral can be written as 1 by function of d comma d dash. Because your given equation can be written as uh, into z of z equal to f of x comma y, equal to f of x comma y. Given equation can be written as, after replacing d by d dash and so on, a function of d comma d dash is z f of x comma y. For z can be written as 1 by function of d comma d. This is particular integral. 1 by function of d comma d dash e power ax plus. So d by a and d dash by b, d dash by b, d dash by b coefficients. Denominator 0, you put on x in the numerator, you differentiate denominator with respect to d partially, and then replace. Okay? That will be the idea. And again, you have to proceed. Here, replacement is d square by minus a square, d dash by minus ab, d dash square by minus b square. This minus is fixed, that is not mingled with the square. This minus is a fixed minus. That will be the idea. Suppose denominator gets AD plus B, LD plus MD form, you have to multiply by conjugate. Take highest power of D. Okay, take highest power of D as common element. Highest power of D as a common element. Highest power of D as a common element. This will be the idea you have to follow. So in that manner, you can. This will be the idea. These are the basic 3 types here. Basic 3 types here. Then Product of these functions, these basic functions, that will be a third, fourth and fifth type here. Fourth and fifth type. Fourth and fifth type. Type 4 is product of exponential with other function. Exponential with type 2 function or type 3 product. For that, you have to replace d by d plus a, d dash by d dash plus b. Okay? D dash plus. Very important that simply exponential. Only exponential means directly replace d by a, d dash by b. In the case of product, you have to replace d by d plus a, d dash by d dash plus b. That is very important. That is very important. Most of the people in the examination may get confusion that whether you have to replace they will directly replace d by a. It means you cannot get any d in the further condition. Okay, further condition. Replace d by a, d by d plus a, d dash by d dash plus b. Then proceed by type 2 or type 3. Proceed by type 2 or type 3. Okay? Type 3 version. When replace d by a, d plus d dash by d dash plus b, d by d plus a, and d dash by d dash plus b. Suppose type 3 is there in the right side, algebraic polynomial. If you have a constant in the 1 by functionality comma d dash, 1 by functionality, if you get any constant, you have to take, instead of highest priority common element, you have to take k, that constant only you have to take as a common element. This will be the idea. Type 5 is any function, any function, any product, other relationship, not in the form of previous 4 types. Previous 4 types. In that case, particular integral can be written as 1 by d minus md dash of f of x comma y. Suppose only one factor. That can be written as integral f of x comma y. You replace y as a what is the factor? A minus mx dx. After integration, you have to write, you can get g of x comma y, g of x comma a, you get a as a y plus mx. That will be the idea. Okay? After integration, you can get only x and a, but again you replace a as a y plus mx, because particular integral you are finding here, it will not involve any arbitrary constant here. Suppose you have more factors here, then you proceed one by one here. Suppose we have d minus m1 d dash. The given equation can be factorized like that here. Then operate with this factor first, and then obtained expression is g of some other way, like this one. You operate this one is this one here, this one, like this procedure, like this procedure. This will be the idea again. These factors can be identified. With the help of the roots of auxiliary equation. The help of the roots of auxiliary equation. This will be the idea you can proceed. This will be the idea you can proceed. Okay. Right. These are the ideas we discussed in the solution of first order, solution of partial differential equations. Partial differential. And more than that, we discussed 2 problems of application yesterday. 2 problems of application. Just go through that application problem also. That 2 problems will be specifically given in that syllabus, or that is enough. These are the conditions you have to consider. Right. Yes, if you have any doubt in this session, you can ask. Tomorrow I will give